Yeah, thank you. Welcome back from the lunch break. I'm happy to be here finally, and I'm really teased by this conference, so I'm hoping for very many nice talks and discussions the next days. But I'm also happy to be talking to you very early, so then you can approach me quite easily if you want to know more. And I talk about some aspects of explainability to machine learning results. So, I mean, we all know that we can do a lot of things with machine learning. We can have machine learning in all areas of our life. But there is always a matter of accepting what a machine will finally tell you. And I mean, if your body measure machine tells you you have to walk 5,000 steps more this day, you want to know where does it come from and should I really do it or can I just continue resting? Same is for the natural scientists. We can also more easily accept what a machine is predicting for us if we have it explained in terms that we know. And these terms that we know from our education, basic education on physical concepts, is what is called the ground truth. And that is what we want to compare our machine learning result to, so that we can really learn the same things from the machine learning, not just the prediction, but also the why. The other part is on spectroscopy learning. So here the background is that I used to be working in Helmholtz-Zentrum Berlin, where we have a radiation source. So for the spectroscopy, we are always targeting larger and larger systems. The experimentalists are having more and more complicated spectra that they measure, and we can do the calculations for small molecules, but ultimately we probably want to use even experimental data to do spectroscopy predictions. So that is on the other half of what this talk is about, and to make with machine learning some efficiency possible, calculations possible that are probably not possible nowadays. I mean, I don't show you the big molecules here. We are just on the way to going there. All right, so I said I worked, or still working, in Helmholtz-Zentrum Berlin, where we run the DESY 2, so that is why I got a connection to the X-ray absorption spectroscopy and other flavors of X-ray spectroscopy. I'm also talking about a data set today for which we do optical predictions, that is excitation spectra. Which are actually unmeasurable, so it's basically orbitals. And then I tell you how we do a graph neural network learning for the respective molecules, and compare with the performance of different graph neural networks. The first step that we took was to analyze at all the prediction, like seeing what effects do we have from different functional groups in them. But we wanted to go further and go to an understanding, because we could up to that moment only understand the peaks by looking into the quantum chemistry result. And that's not what we want if we want to use machine learning exclusively. All right, so let's get started. The machine learning of the spectra in themselves. So here are the data sets. It's a QM9 organic molecules data set. You see molecules that are quite funny, some of them, so you wouldn't consider them as necessarily so stable, but I mean, they're in there. It has a 9 in its name because you have 9 heavy atoms at the most, and heavy means everything that's not hydrogen. And the original data set had like single-valued data collected of all of these molecules, while there has been a modification, QM9 star, that had theoretical orbital transition spectra, which I said they are artificial, but I mean you see here funny energies as well. It's like the orbitals you excite from or you excite into, but still it was instrumental for doing the machine learning. We have small molecules, we have a large data set, so we could set up the methods here. And then we developed an own XAS data set from roughly half of the molecules of the original QM9, so that are carbon KH X-ray absorption spectra. Yeah, so and why spectroscopy and what is the interesting part here for machine learning and to conceptualize this idea is, I mean, you have a spectrum, here is the X-ray absorption, of a specific molecule, and that's really a clear fingerprint of the molecule. And it's different for every other molecule. So that's why you have, if you take the molecule as an input and the spectrum as an output, that is where you have your one-to-one correspondence, so you can do the learning of this property. In quantum chemistry, of course, you get line spectra shown in blue here, and the line spectra correspond also to combinations of orbitals into which or from which you are exciting. So you have numbers of orbitals assigned, or also combinations of orbitals assigned to each of these signals. So that is our ground truth, where we know exactly what is happening from the quantum chemistry calculation. The disadvantage is if you do this for something larger than these, I didn't show the molecules, here's one, for the small organic molecules, it takes you quite a long time. Probably you cannot do the calculation. Okay, so with the idea that we have a one-to-one correspondence between molecular structure and output, we can devise a neural network that is sitting here in between. And particularly what we used was a graph neural network or a message passing neural network. So in this one, the chemical structure, each atom becomes a node of our neural network, each bond becomes an edge of our neural network. Then we go into the message passing, so these are different hidden layers of this neural network in which we are updating the information, which is basically, I mean, we want to compute the spectrum here, so the information that we transfer through the neural network is, now I need a spectrum, is for a certain energy position of the spectrum, and here we did some binning so that we have just 300 points evenly distributed. For each of these energies, we are collecting in the neural network weights in the end, and like contributions of the different atoms, by updating on one atom at this energy the information that is given from the neighboring atoms, and measure it against the reference spectrum. So we have many updating steps, and then ultimately we end up with a learned spectrum. The reference is used in a way that we define the relative spectral error. You can visually see the difference already. I mean, what we compute is the difference between the two curves on the energy steps that we've chosen. That is 300 different points here, this binning that I just mentioned. And we have some very good predictions and some really bad predictions. You see it with the bare eye, and we can numerically keep this tracked. So for the X-ray spectroscopy data set, we tested 3 different neural networks, of which GAT-VT, one of the networks that has edge information in itself, performed the best. It's up here. So here you see the average relative spectral error, RSE, and that the outliers you have towards larger RSE values, and you see also for every of these methods an example of one of the best predictions and one of the worst predictions. So, I mean, and this is probably something like here you don't really want to work with, whereas these ones here, they look quite okay. Here we have a bit little resolution. So, I mean, the numbers speak for themselves, but we can have good predictions. We are happy with the quality. The analysis, however, was done on the QM star, QM9 star data set, because here we even had some other work by the developers of this data set who used one of the straightforward message passing methods, and their result is shown in blue, while ours is shown in orange. And of course, I mean, there are always new neural networks available. So SNET is one of the popular, or I think it's competed already again. But at the time we wrote the paper, this was like the most state-of-the-art. It knows edge information, and it knows a little bit of the density variation over the molecule. So that's why it performs best here. And in the following, we analyzed mostly the results for SNET. Also, numerically, it had the best results. So here's the RSE given. And the reference, finally, it was calculated for a super long time. So the training was very long. We didn't really find out why this was. Right. So now we come to the analysis of the neural networks. This is quite short because there is more fancy stuff to follow after this analysis. But I mean, we had a little bit of look on how does the neural network correspond to the number of heavy atoms. So in these violin plots, you see that for the lighter structures, and here's a mass representation that shows basically the same, but a little bit different. You see that the RSE has quite some spread, but there's also not so much data for smaller structures with only 6 heavy atoms. While you see then that you get more and more outliers, the heavier you become in your calculation, so the more non-hydrogen atoms you have, while the average is getting denser and has a smaller variance in itself. So, okay, we see some connection with the weight of the molecule. More interestingly, we saw a connection with the functional groups that we have. And like the weight, that depends on how frequent do we have a functional group at the most. I mean, it's not everything. Here in this t-test grouping, if we look at the SNET, the red examples, or in all, the red examples are the ones that are difficult to predict, while the blue examples are the ones that are most easy to predict. And you can already look here in parentheses, you see how many, the percentage of how often this functional group appears in the data set. And then the turning from red to blue speaks for itself because it correlates more or less with the frequency of occurrence in the data set. So this is very clear. And from this you can say that ether and alkyne and aldehyde are always easy to predict. But we did something more, which was a bit, this was not really something we quantified in a representation like calculation like this, but that you can see well from these maximum RSE structures, and we also had them cataloged in a viewing graph where we could easily identify which molecules there are. If you look closely, I don't know, it's for the ones up there it's maybe difficult, but if you look closely here, you have NH2 plus, NH3 plus here, you have O minus here, and you have this in basically all structures. So definitely something is missing. about the structures, and that is the charge. So we didn't include a charge in the neural network. I think we haven't been fully aware that there are Zwitter ionic species in the setup from the onset. So in the end, these are the ones that make calculations difficult, and they push through, especially also for these smaller, less often occurring structures. All right, so this is the straightforward analysis, but I mean, we want to really understand the spectra no matter what. I mean, it doesn't help us that we get a nice prediction of the spectrum when the prediction doesn't help us to tell the experimentalist what compound he or she has measured. Then our prediction is useless. Then we don't have to do it at all. I mean, with a compound, yes, we can help a little bit, but that's not yet a peak assignment. So what we want is really to know what is behind these spectral lines, or underneath the broader peaks that we would fit over them and that we would align with the experimental spectrum. So the human spectroscopist, of course, knowing some theoretical calculations, having a lot of experience with their materials, with their beamlines, with their whatsoever spectrometers, they are very dedicated in assigning peaks, and they have a good base knowledge, but in their life they see maybe 5,000 spectra and interpret maybe 500. Well, I don't know, it's roughly. While a machine can know millions, billions of spectra, everything that's there, and use all this, but can this machine, really know anything about why the spectrum is like this? So let's get into it. It can, definitely. That's what I'm showing you in the last part of the talk, and I still have nicely time to explain all the concepts. So what we want to have is the energies and the intensities. So here's underlying a quantum chemistry again. So in quantum chemistry, you just calculate the peaks with oscillator strength that gives you the lines. So that's easy. In the machine learning, in order to quantify these energies and intensities, we did a binning approach again. So I told you already that we have 300 points. Some of them are taken together so that we assemble them into a peak that would look, for example, here like a Gaussian shape peak. So we collect all the information of the neural network at these energies weighted by this Gaussian that we underfit in order to nail it back to the transition of the line spectrum. And what actually are we doing? What are we looking for is the atom or the orbital contributions. So again, in quantum chemistry, you know this very well. You get these nice orbital shapes, and you know what is in the transition and which orbital is contributing. So you know everything. You know on which atoms the orbitals sit. You're fine. In the machine learning, you can do something very straightforward, but you need to know it. And that's using class activation maps. So that's depicted here. And I mentioned it already when I guided you through the message passing flow chart. In the end, before you have your calculation at one energy, or when you get your result at one energy, you can assign a weight to each atom that is contributing at this particular energy to your peak. So there are some that are not contributing, they get low weights. Others are contributing heavily, they get high weights. And then you can make a threshold to say, okay, those are labeled 1, they are contributing a lot, the others are labeled 0, or you can make this also in intervals, and that's what we're using for the prediction. Okay, here is it, it's shown again, basically what I just said. You accumulate the weights on the nodes. And how does it look? So you are really at one energy here in the center of this green sphere. And at this energy, there's one peak at this point, so that's why we can analyze it more easily. You just plot the weights, the CAM attributions, onto the atoms that are contributing. And you see it's only here the CO double bond that's important, and maybe the neighboring carbon a little bit. Okay, so we project back the weights on the input, and we compare this to what we have in our ground truths. That's the orbitals. So the orbitals are also mapped according to their atomic, to their molecular population of the respective state. They are mapped back onto the atom that is contributing to the orbital, and then we see, okay, the donor orbital is over here, this carbon atom, so it's a 1s, of course, 1s orbital, and the acceptor is this double bond, so pi star. And that's, if you put this on top of each other, I mean, you get the relative weight is not in here, but you get the same structure. So you would say, this is cool, this is matching. And this was super fascinating when we saw in so many examples how nicely this is matching. I mean, this is something we had tested on the other data set, and then we didn't quantify it for a long time, but it's really amazing. I like it a lot, these explanations. You can also quantify this, because, I mean, to make this numerical, you need to have a scoring scheme. And this is the area under the curve routine. It's not used, I think in machine learning it's used sometimes. We got it from, I don't know which other discipline, but it's basically comparing these results and this one, and giving you one if there's a matching, and otherwise if there's no matching, it gives you a 0. So we get quite far with that. And then you can also, to get some intuition, I mean, I always like to look at the structures to really explain things and understand things. Here's an example of where we have a good prediction, so an area where the two curves are really matching. And you see here that we get close to 1. For the core orbitals, we are always a bit better than for the virtual orbitals because they are more localized anyway. Here we have a bad example, like where the two curves are not so well matching. And you see the differences already virtually. I mean, this one, for example, is not seen at all in the CAM, but it's important in the quantum chemistry. Yeah. And then we also collected all the CAM values over the complete data set for the different methods. It turned out, again, that the GAT-V2 was quite promising, especially if we plotted this as a function of the RSE. So on the left-hand side, we have small RSE values. On the right-hand side, we have large ones. And you see that the predictions are the better the closer we are to the ground, to the reference spectrum, and they are getting worse. But there's also graph neural networks that cannot do. I mean, they do statistically in this way. Then we tested some other things. So we wanted to know. We have done the ground truth for the entire peak, but we can look at the different line spectra and look only at this energy. That is what we plot here. And we can really see that even each underlying transition, that the first two ones, they go into the CN triple bond, while the first one goes into, what is it? A carbon-nitrogen double bond. So we see also this difference in the CAM and in the orbitals. Here plotted really as orbitals and not as mapped orbitals. And then we also looked into local and global effects. So here's the full prediction. which is done in quantum chemistry atom by atom. So we have in black atom-wise spectra, and the same we do with the CUM. We just compute the CUM score at a specific atom, at the one we look at, and plot the CUM score for each energy. And then you see in some cases we get a really nice matching, at least in the beginning, but you see that the CUM has, due to this like edge information, a little bit less potential to really do atomic resolution at the higher energy end of the spectrum. So here is definitely one limitation of the analysis, but normally you don't compare atom-wise spectra. Yeah, and the final tests were on robustness. So we have an RSE increase if we add functional groups and do the learning based on what we learned before. So we get the perturbed structures with much higher RSE. They also get a much lower AUG score. So this is a difference in AUG. The reason is because we added a 10th atom to the 9 heavy atom data set, so it's also not so surprising that here you run into a limit that you may want to overcome at some point. And finally, we looked into distortion effects, and here we want to see the GUT-V2 mostly, which is where? I don't see it. I think I cutted it away. No, this is the distortion. It's all the GUT-V2. So, so we see that for TDDFT, our reference, we don't see any changes for small distortions. The first change is already at small distortions, so extending sizes. We see nothing of this in the GUT-V2 because it just learns as if there was no distortion, so we get some error increase and also limitation of robustness here if we don't do it included in the learning. Yeah, so that was all I wanted to show you, mainly how we do machine learning for spectroscopy data, analyze it by functional groups, and then by really understanding spectroscopy. The work was done still back in Berlin, mostly by Kanishka Singh and a cooperation partner. Yeah, thanks for listening.
Thank you very much. I imagine we have a few questions.
Yes, thank you for the nice presentation. So your CUMs have these more density-like lobes. Is there a way to introduce phase to have something more orbital-like?
Yeah, I mean, we went to the atom information, but yeah, there might be. So, but we haven't started into looking more into the orbital thing. I mean, there is a sign definitely in there, but
yeah, maybe pairwise contributions or something like that.
Yeah, we should.
One more question.
Thankfully, nobody threw it at me this time. Thanks. I just wanted to ask, so the attention mechanism allows you to back out again the transition type of matrix elements and how the contributions of different orbitals come approximatively. And so you've learned the spectrum on a grid. Have you tried learning it directly on the transition peaks?
No.
Because then you get this information free, right?
Yes, there were two reasons why, or there was basically one reason why we didn't do it. I mean, the original paper from which we had our first try to do the same thing and then see what we can improve on this. They had done this comparison, line spectra versus band spectrum, but on the other hand, we had the philosophy that we would want to do this on experimental data. So we wanted a method that can be done on every spectrum you have. Also spectra from different methods without evaluating on the method at all.
But then you need to have comparable lifetime processes that broaden your spectrum.
Yeah, I mean, but you need to have everything comparable. Yeah. I mean, if you start mixing theory methods, you're also getting a mess. So, but I mean, if you have a lot of data, maybe that doesn't hurt.
I think it's time to go on for the next speaker. Let's thank the